Listen to me very carefully. I'm not going to take much of your time, but what you're about to hear could completely change how you see humanity's future. For thousands of years, we looked at the stars and wondered, could we ever reach them? Today, I'm telling you something extraordinary. The next giant leap in human space travel will not be a rocket, it will be an idea. And once that idea becomes reality, the universe will no longer be out of reach. For over 100 years, human beings have relied on a surprisingly primitive idea to reach space: controlled explosions. We strap ourselves to massive cylinders filled with fuel, ignite them, and hope the mathematics holds. This approach worked. It carried us to the moon, placed satellites in orbit, and opened the door to the cosmos, but it is also deeply inefficient. Every launch discards most of the vehicle, wastes enormous energy fighting gravity, and limits how far and how long we can travel. This is why the next giant leap in space exploration will not come from making bigger rockets, but from abandoning the rocket age altogether. We are now standing at the edge of a quiet revolution in propulsion. Instead of explosive force, the future belongs to continuous, precise, and elegant systems. Plasma engines, for example, do not burn fuel in a violent burst. They use electricity to ionize gas, creating a stream of charged particles that can be accelerated to incredible speeds. The thrust may be gentle, almost delicate, but it is constant. Over weeks and months, that steady push builds up velocities far beyond what chemical rockets can achieve. This means spacecraft that can reach the outer planets faster, maneuver more precisely, and carry out missions that were once impossible. It is the difference between sprinting and running a marathon. The latter may seem slower at first, but it ultimately goes much farther. Ion drives already exist, and they are not experimental fantasies. They have powered probes that visited asteroids and distant worlds, operating for years with remarkable efficiency. What makes this so transformative is that space is a vacuum. Once you are free from Earth's gravity well, even the smallest force, applied continuously, becomes immensely powerful. This insight reshapes how we think about travel beyond Earth. Spacecraft of the future will no longer be limited by brief moments of thrust. They will glide through the solar system, constantly accelerating, constantly adjusting, like sailboats riding an invisible cosmic wind. Alongside plasma and ion technologies, nuclear propulsion represents another step away from chemical rockets. Nuclear systems tap into the same forces that power the stars, releasing millions of times more energy than chemical reactions. A nuclear-powered spacecraft could cut travel times to Mars dramatically, reducing journeys from months to weeks. This is not merely a convenience, it could be the difference between life and death for astronauts exposed to radiation and microgravity for extended periods. By shortening travel time, we reduce risk, increase mission success, and make human exploration far more realistic. The physics is sound, the engineering challenges are enormous, but the destination is clear. What all of this signals is a profound shift in mindset. We are moving from brute force engineering to intelligent design. Instead of overpowering nature, we are learning how to work with it. The next era of space travel will be quieter, more efficient, and far more ambitious. When future historians look back, they may say that the true breakthrough was not a single mission or discovery, but the moment humanity realized that explosions were no longer the answer. This technological transformation leads naturally to the second great change: space travel becoming routine. Right now, every launch feels historic, dramatic, and rare. Cameras roll, crowds gather, and we hold our breath. That sense of spectacle exists because launches are expensive, risky, and largely non-reusable. But history shows us a pattern. When a technology is new, it is fragile and exclusive. When it matures, it becomes invisible. Air travel once inspired awe and fear. Today, it is an everyday experience. Space will follow the same path. The key to this shift lies in reusability. A rocket thrown away after a single flight is like an airplane discarded after one journey across the ocean. It makes no economic sense. Reusable spacecraft change the equation entirely. By landing, refueling, and flying again, launch costs plummet. When cost decreases, frequency increases. When frequency increases, innovation accelerates. Suddenly, Space is no longer the domain of superpowers and billion-dollar budgets. It becomes a laboratory, a workplace, and eventually a destination. As space travel becomes routine, the psychology of exploration changes. Engineers stop designing one-of-a-kind machines and begin building fleets. Scientists stop waiting years for a single mission and start planning sequences of experiments. Students grow up knowing that reaching orbit is not a miracle, but a career path. This normalization is crucial because the greatest leaps in progress happen when access expands. When more minds can participate, ideas multiply. Routine access to space also unlocks infrastructure. Space stations evolve from isolated outposts into hubs. Orbital factories begin producing materials impossible to create on Earth, using microgravity as a tool rather than an obstacle. Fuel depots appear in orbit, allowing spacecraft to refuel without returning home. Each of these developments feeds the next, creating a self-sustaining ecosystem beyond our planet. Space ceases to be a distant frontier and becomes an extension of human civilization. Perhaps most importantly, routine space travel reshapes our sense of time. When launches are rare, we think in terms of decades. When they are common, we think in years, then months. Progress accelerates not because the laws of physics change, but because human behavior does. We take more risks, test more ideas, and learn faster. This is how technological revolutions truly unfold, not in sudden explosions, but in steady compounding advances that eventually become unstoppable. In this emerging reality, the stars no longer feel unreachable. They feel postponed, waiting for the final pieces to fall into place. Leaving the rocket age behind and making space travel routine are not separate goals. They are two halves of the same transformation. One changes how we move through space. The other changes how often we do it. Together, they mark the moment when humanity stops visiting space and starts living with it, even if we don't yet realize that this quiet transition is already underway. For most of human history, the idea of living beyond Earth belonged entirely to myth and imagination. The moon was a symbol, Mars a god, and the stars untouchable points of light. Yet the moment we first left our planet, even briefly, something fundamental changed. Earth was revealed as a single, fragile world floating in a vast cosmic ocean. From that perspective, remaining confined to one planet no longer looks like destiny, but limitation. Becoming a multi-planet species is not an act of arrogance, it is a continuation of a very old survival strategy. Life expands or it disappears. The first step away from Earth will not be dramatic colonies under glass domes scattered across alien landscapes. It will be slow, practical, and methodical. The moon, just days away, will become our training ground. There we will learn how to build with local materials, extract water from rock, and generate energy in environments with extreme temperature swings. These are not glamorous achievements, but they are essential. Civilization is built not by grand gestures, but by mastering logistics. Every lesson learned on the moon prepares us for Mars, and every mistake made close to home prevents catastrophe. Farther out, Mars represents a turning point. It is distant enough to force independence, yet familiar enough to feel achievable. Establishing a human presence there changes our relationship with extinction. A single planet species lives under a constant, invisible threat: asteroids, pandemics, climate instability. A multi-planet species gains resilience. History on Earth shows this pattern repeatedly. Populations that spread out survive upheaval better than those that remain concentrated. On a cosmic scale, the same logic applies. Space colonization is not an escape from Earth's problems, it is insurance against their finality. As humans settle beyond Earth, evolution itself begins to diverge. Different gravity levels, radiation environments, and day-night cycles subtly shape biology and culture. Over generations, space-borne humans may adapt in ways we can barely imagine. This is not the end of humanity, but its branching. Just as ancient migrations produced diverse cultures and civilizations, space will produce new variations of what it means to be human. The stars will not erase our identity, they will multiply it. But this expansion cannot happen through human effort alone. Space is harsh, unforgiving, and indifferent. This is where artificial intelligence enters not as a tool, but as a partner. Human beings are remarkable, but we are also fragile. Our bodies evolved for Earth, not for radiation storms, vacuum, or decades of isolation. Machines do not suffer fatigue, fear, or biological limits. In the future of space exploration, intelligence that does not breathe will go where humans cannot. AI will be the first explorer on nearly every frontier. Long before a human steps onto a distant moon or asteroid, intelligent systems will map it, analyze it, and understand its risks. These systems will make decisions in real time, adapting to unexpected conditions faster than any human could. In deep space, where communication delays stretch to minutes or hours, autonomy is not optional. AI will think, act, and solve problems independently, becoming the advanced consciousness of humanity. Beyond exploration, artificial intelligence will build the foundations of off-world life. Autonomous machines will assemble habitats, mine resources, and maintain life support systems long before humans arrive. This changes the entire economics of space colonization. Instead of sending large crews into danger, we send intelligence first. By the time humans follow, the environment is safer, more predictable, and already partially adapted for life. Space stops being a hostile unknown and becomes a prepared environment. The relationship between humans and AI in space will be deeply collaborative. Machines excel at precision, pattern recognition, and endurance. Humans excel at creativity, intuition, and meaning. Together they form a system far more capable than either alone. In this partnership, astronauts become explorers and decision makers rather than maintenance workers. Their role shifts from survival to discovery. The machine handles the danger, the human asks the questions. There is also a profound psychological dimension to this collaboration. Knowing that intelligent systems are constantly monitoring, repairing, and predicting failures changes how humans experience isolation. Space no longer feels empty when intelligence surrounds you, even if it is artificial. In this way, AI becomes not just a tool, but a companion and extension of human presence stretched across vast distances. As we spread to other worlds with the help of intelligent machines, a new pattern emerges. Humanity becomes less tied to a single location and more defined by its ability to adapt. Intelligence, not geography, becomes our true home. Planets turn into platforms, and space itself becomes a medium through which civilization flows. This is not the end of Earth's importance, but the beginning of its role as the birthplace of a species that learned how to survive beyond its cradle. What unfolds from this moment is not a sudden leap, but a steady transformation. One base becomes two, then many. One AI becomes a network. One planet becomes several. At no single point does the universe suddenly feel conquered. Yet at every step it feels more accessible. The future of space is not a dramatic exodus, but a quiet expansion guided by intelligence, patience, and the recognition that survival and curiosity are two sides of the same cosmic instinct. For centuries, faster-than-light travel and wormholes were considered the domain of science fiction, a whimsical escape for imaginative minds. Even in the early 20th century, the notion of moving beyond the speed of light was dismissed as impossible, forbidden by the very fabric of physics. Yet today, theoretical frameworks suggest otherwise. Einstein's equations do not prohibit the concept of warp drives. They only define the conditions under which space and time interact. In a sense, the universe is not as rigid as once imagined. Space itself can stretch, warp, and bend, allowing distances to shrink in ways that might make what was once impossible achievable. These ideas are not wild speculations. They emerge from legitimate mathematics and general relativity disciplines that have been rigorously tested for over a century. Scientists now ask not whether faster-than-light travel is allowed by physics, but how it might be engineered. This subtle shift in perspective transforms the dream into a tangible frontier for research and experimentation. The implications are staggering. If we can manipulate space rather than merely move through it, entire solar systems become accessible within human lifetimes. A ship could, in theory, reach distant stars without violating the local speed of light, because it is the space itself that moves, carrying the vessel along like a conveyor belt. This is a radical departure from conventional thinking. For generations, exploration was constrained by the limits of propulsion, fuel, and human endurance. Now, the constraints may lie in geometry and energy, questions of curvature rather than combustion. The exploration of these possibilities requires not only imagination but also a mastery of mathematics and quantum physics. It demands that we stretch our minds to perceive the universe not as a static backdrop, but as a dynamic, malleable medium in which new paths can be forged. This shift in perspective affects more than just propulsion. It changes the way humanity conceptualizes the universe itself. Once we thought of the cosmos as a vast, empty void punctuated by stars and planets at fixed distances. And today we understand that space is a fabric, flexible and interconnected, responsive to energy and matter. Black holes, once feared as cosmic vacuums, are now understood as regions where space-time curves so intensely that new phenomena emerge: wormholes, singularities, and perhaps bridges between regions of the universe. The study of these phenomena is no longer an abstract mathematical exercise. Each insight has practical implications for navigation, energy, and the future of human exploration. What was once an obstacle distance, isolation, the tyranny of light speed, can now be reframed as an opportunity to innovate, to discover, and to extend the reach of our civilization. As humans venture further into space, the concept of identity begins to evolve. No longer confined to a single planet, humanity will be defined not by geography, but by a shared curiosity and collective intelligence. This evolution is mirrored by the machines that accompany us. Intelligent systems capable of independent thought, decision-making, and adaptation. These artificial companions will explore the most dangerous and remote regions, charting unknown territories, analyzing data, and preparing environments for human arrival. They do not tire, they do not fear, and they can operate in conditions that would immediately endanger a human crew. In doing so, they extend the capabilities of the human species, acting as both scouts and protectors, ensuring that when humans do arrive, the environment is understood and partially tamed. The collaboration between human ingenuity and machine intelligence becomes the defining feature of interstellar exploration. The expansion of human consciousness into space also brings a profound philosophical shift. When humanity leaves Earth in earnest, it becomes clear that our civilization is not bound by a single ecosystem or a single fate. The idea that we are fragile, that extinction is imminent, is counterbalanced by our ability to extend life across multiple worlds. This changes the very psychology of human society. Where once risk was intolerable, it becomes calculated. Where once distance felt insurmountable, it becomes manageable. Our perception of scale transforms. We begin to think not in terms of decades or centuries, but in terms of light years and millennia. This reorientation affects science, culture, and governance. Policies are shaped by long-term considerations. Scientific research is guided by multi-generational goals, and human ambition is elevated to a cosmic scale. As exploration progresses, discovery accelerates exponentially. Each new planet, asteroid, or moon surveyed provides data that informs the next mission. Each insight into cosmic phenomena, from the behavior of matter near a black hole to the structure of interstellar magnetic fields, creates new opportunities for engineering, energy generation, and understanding life itself. The first observations lead to hypotheses. The hypotheses lead to experiments. The experiments produce technologies that redefine what is possible. The iterative cycle of exploration and discovery creates a self-reinforcing momentum, where the expansion into space feeds scientific advancement, and scientific advancement fuels further expansion. The result is a civilization that evolves not just on Earth, but throughout the solar system, and eventually across interstellar distances. There is also a profound social and cultural dimension to this expansion. As humans become a multi-planet species, the notion of nationality begins to blur. Shared challenges in space radiation, isolation, resource scarcity require cooperation at a scale that surpasses any terrestrial alliance. Astronauts, engineers, and scientists from diverse backgrounds must collaborate seamlessly, guided by shared objectives rather than local interests. This necessity fosters a sense of unity and purpose, reinforcing the idea that humanity is a species defined by curiosity and resilience rather than by borders or politics. Cultural exchange becomes inevitable, and the values that emerge in these new environments may ultimately influence life back on Earth, creating a feedback loop between planetary and cosmic civilization. The technological foundations of this expansion rest not only on propulsion but also on materials, energy systems, and life support. Spacecraft must withstand radiation, temperature extremes, and the vacuum of space. Habitats must be self-sustaining, capable of recycling air, water, and nutrients. Energy must be generated efficiently, often using solar arrays, nuclear reactors, or advanced fusion systems. Each solution is a complex puzzle, but solving it multiplies the potential for human expansion. The more we learn to live off Earth, the more capable we become of exploring the stars. Each advance in one field, propulsion, AI, life support enables leaps in the others, creating a network of interdependent technologies that collectively redefine the limits of human capability. Psychology also plays a crucial role. Humans are adapted to life on a single, relatively stable planet. Isolation, confinement, and prolonged exposure to microgravity present enormous challenges. Here again, intelligent systems provide solutions. AI companions monitor health, predict psychological stress, and offer companionship, mitigating the risks of long-duration missions. They create a buffer between humans and the unforgiving environment of space. By extending cognition and perception, these systems allow humans to operate effectively at scales and distances previously unimaginable. In doing so, they not only facilitate survival, but also enable creativity, curiosity, and discovery in environments that would otherwise be hostile and overwhelming. As we probe the universe using these tools, our understanding of fundamental physics will deepen. Questions about the nature of dark matter, the behavior of gravity at extreme scales, and the topology of the cosmos itself will be informed by empirical observation and experimentation in environments previously inaccessible. Every mission beyond Earth is simultaneously a laboratory and a telescope, offering data that challenge long-held assumptions and open new theoretical frontiers. The act of traveling, exploring, and inhabiting new worlds is therefore inseparable from the expansion of human knowledge. Space becomes both the stage for human civilization and the proving ground for the deepest questions about reality. As humanity begins to extend its reach beyond Earth, one of the most profound transformations will occur not in technology, not in infrastructure, but in the human mind itself. For generations, we have imagined space as distant, inhospitable, and beyond our grasp. These beliefs have shaped not only our ambitions, but also our limitations. The greatest barrier to interstellar exploration is not the scarcity of fuel, the fragility of materials, or the endurance of the human body. It is the fear embedded in our consciousness. Fear of failure, fear of the unknown, fear of leaving everything familiar behind. Overcoming these mental barriers is the first step toward realizing the potential of the cosmos. Once we accept that the universe is not a distant spectacle, but a domain to be navigated, humanity begins to act differently. Our species become not merely observers of the stars, but participants in their unfolding drama. This psychological leap, subtle as it may seem, is as critical as any technological breakthrough. The human mind is remarkably adaptive, yet it is often constrained by assumptions and deeply ingrained perceptions. On Earth, gravity, atmosphere, and the passage of time condition our experience, influencing our expectations and shaping our definitions of what is possible. In space, these assumptions are challenged. When astronauts experience weightlessness, isolation, and extended periods of sensory monotony, they confront limitations that are both physical and psychological. This confrontation has historically led to breakthroughs not just in survival, but in understanding. Humans learn to operate under conditions that were previously unimaginable, expanding cognitive frameworks and problem-solving abilities. This process is incremental but cumulative, each mission building resilience, confidence, and a new mental model for operating in a universe that does not conform to terrestrial norms. Once psychological barriers are overcome, the implications for exploration multiply. Fear and hesitation are replaced by calculated risk-taking and innovation. The human mind begins to conceive of solutions that were once dismissed as fantastical. Habitats become more than protective shells. They evolve into adaptive ecosystems that integrate biology, engineering, and energy in ways that allow humans to flourish. Propulsion systems are no longer limited by previous constraints. They are designed with creativity and long-term objectives in mind. Artificial intelligence, once a tool, becomes a collaborator in discovery capable of autonomous operation in environments that humans cannot endure. Together, human intellect and machine intelligence redefine what is achievable, demonstrating that the limits imposed by fear were always psychological rather than physical. This psychological readiness also affects collaboration and governance. As humans expand to multiple worlds, cooperation becomes essential. The challenges of establishing off-world colonies, resource management, life support, communication across vast distances cannot be addressed by individuals or isolated teams. They require collective problem solving at unprecedented scales. The shift from fear-based limitation to confidence-based initiative transforms societal structures, encouraging collaboration across cultures, nations, and disciplines. Leadership becomes less about authority and more about coordination, innovation, and adaptability. A multi-planet civilization necessitates a mindset attuned to complexity, long-term consequences, and ethical responsibility, all guided by the recognition that humanity's survival and expansion are interdependent. As exploration extends into new territories, the process of discovery accelerates. Every planet surveyed, every asteroid mapped, and every distant star observed adds layers of knowledge that inform the next mission. Each discovery raises new questions about the origin of life, the nature of dark matter, the mechanics of black holes, and the structure of the cosmos itself. This iterative process is exponential. A single breakthrough in propulsion or habitat design can enable investigations into regions of space previously inaccessible. The universe thus becomes a dynamic laboratory, where every observation contributes to both immediate practical applications and profound theoretical understanding. Humanity's intellectual and technological growth becomes intertwined with its physical expansion, reinforcing a cycle of exploration and discovery that is self-sustaining. The acceleration of discovery also has a transformative effect on culture and education. The next generation of humans will grow up not only with the knowledge that space travel is possible, but with direct exposure to its realities. Children will witness autonomous spacecraft navigating asteroid belts, habitats functioning on other planets, and artificial intelligence collaborating with humans to solve problems in real time. This exposure reshapes aspirations, broadens imagination, and instills a global consciousness oriented toward exploration and innovation. Education becomes experiential and iterative, blending the abstract and the concrete. Scientific inquiry is no longer confined to textbooks, it is embedded in the lived experience of a civilization actively participating in the cosmos. The technological and psychological frameworks developed for space exploration will also feed back into life on Earth, transforming industries, infrastructure, and society itself. Advances in energy efficiency, materials science, robotics, and artificial intelligence developed for survival in extreme environments can be adapted to address terrestrial challenges. Water purification, renewable energy, automated systems, and remote medical technologies all benefit from the constraints of off-world design. Humanity's relationship with its home planet evolves alongside its expansion into space. Learning to live sustainably in isolated, resource-limited environments informs strategies for managing Earth's own ecological systems. In this way, the act of reaching beyond Earth simultaneously enhances our capacity to thrive on it. As humans continue this outward journey, the very notion of identity evolves. We are no longer defined solely by geography, nationality, or culture. We are increasingly defined by our ability to understand, adapt, and expand our presence across the universe. This expanded identity shapes ethics, philosophy, and governance. Questions that were once abstract about the value of life, the ethics of artificial intelligence, or the limits of exploration become immediate and concrete. Decisions made on one planet have ramifications on others, necessitating foresight, responsibility, and a long-term perspective that transcends individual lifespans. humanity begins to operate not just as a species bound to a single world, but as an intelligent, conscious force capable of shaping its own trajectory across the stars. This transition from terrestrial beings to a multi-planet species is gradual yet relentless. It begins in the mind, in the willingness to imagine that humans can survive, adapt, and thrive beyond Earth. It manifests in incremental technological innovations, the development of intelligent systems, and the establishment of infrastructure across multiple worlds. And it culminates in a civilization that redefines what it means to be human, capable of living among the stars while preserving the curiosity, creativity, and resilience that allowed the first leap off Earth to succeed. The greatest challenges remain not in the material obstacles of space, but in cultivating the mental, ethical, and collaborative frameworks necessary to transform possibility into reality. In this way, exploration is as much an inward journey as an outward one, expanding both the mind and the reach of humanity simultaneously. And so, as we stand at the threshold of this incredible journey, it becomes clear that the next giant leap in human space travel is not just about rockets, technology, or distant planets. It is about the human spirit, our curiosity, and our willingness to challenge the limits of what we believe is possible. Every step we take beyond Earth expands not only our reach into the cosmos, but also our understanding of ourselves, our potential, and our place in the universe. By embracing innovation, collaboration, and the courage to imagine, humanity will transform from a species confined to a single planet into one capable of exploring, thriving, and even living among the stars. Thank you for joining me on this journey of discovery. Your curiosity and passion for the cosmos are what drive these conversations forward. And together, we can continue to explore the infinite possibilities that await.